There we go. So, then you know what? I lost my pen. There it is. So welcome to chemistry. And yeah, even I keep going in and out of focus in this little blurb over here. So chemistry is the study, is usually talked about as it's a study of matter. You don't need to know that. A video I posted today that's for your lab gives a brief history of the building blocks of matter, and you just have to listen to the video and hopefully get you just write 1 to 2 paragraphs about your thoughts. Everybody's going to have a different piece of that video that inspires them in some way. It depends on where you are. If you watched it today, if you watched it on Friday, it would be a different piece because we're in a different place. It could be the initial part I talk about Democritus, who's one of the ancient Greeks, and their idea of the elements, that we had building blocks, and that is air, earth, water, and fire, and ether, which is the transformative part. So chemistry is traditionally talked about as the study of matter. The real question becomes, what is matter? And so matter is the physical stuff, is how it's usually described. Now, something you'll see, and I forgot to mention this earlier, there's actually 3 videos posted at this point for your class. One is, I usually the first day, the last half hour, I do a talk on chemistry and health, and it's a healthy change challenge. And so it's for the month of October. Last year, the year before, was the first time I did it, and I was amazed how many people took me up on it. You get several, like 4 to 5 bonus points. You can even bring somebody else in to do it with you, like your mom or your brother or your partner, and you make a healthy change for a month. So that video is up there. And then I posted a video that's for the lab, and you watch it and it goes through the history. And the other video is like a pre-video for Wednesday's class. It's a pre-lecture. It's about sig figs and math, and we'll talk about that more on Wednesday. But matter is the physical stuff. It turns out where this all comes from is quantum mechanics, which we actually get to. I think it's the 5th lecture. We talk about quantum mechanics, and we're actually vibrational beings. Everything is vibrations, and it's the vibrations that creates the matter. So chemistry is usually taught as everything is about the matter, the physical stuff. That's how we all believe everything is. But the physical stuff comes from your thoughts, your beliefs, which creates vibrations. So we'll get to that as I talk about Rutherford. J.J. Thompson discovered the first subatomic particles, which we're going to talk about here today. But Ernest Rutherford, I have space there. I was hoping I wasn't blurry until I moved something. Go figure. It's the gnomes. The gnomes had me. So Ernest Rutherford, you don't need to know any of the history and the names. You just have to have an appreciation for it. He did an experiment in which he sent what are called alpha particles. So that fish is an alpha, and so these particles have a +2 charge. So things in nature are either neutral, positive, or negative charge, and we'll see that when we get to the subatomics. And it had a mass of 4 AMUs. So an AMU stands for atomic mass unit. It's something I mentioned in the video. When we're at the atomic scale, things are really tiny, like 10 to the -22nd, 24th power, meaning you have a 0 point and then 24 zeros before you get to a number. Like, how can they even figure that out? There's a guy who actually will possibly be one of the youngest Nobel laureates. He's been nominated, but he figured out the mass of the proton, and they kept telling him he was wrong. This is very recently, and it turns out he was right. He did it in a very different way. Anyway, so he took these alpha particles. Ernest Rutherford actually got a Nobel Prize for his study with alpha particles. At the Nobel Prize, when he received it, he received it in chemistry and not physics, even though he was a physicist. And he said, well, that's the fastest anybody became a chemist. And the Nobel Prize Committee didn't like that, and so they didn't give him a prize for this. But he sent it out a piece of gold. So here's a question. What's the symbol for gold, right? Periodic table. Here it is. And so you may know. You can like push your thing, your space bar, and tell me.
Isn't it AU?
It's AU.
It is AU. AU stands for, does anybody know what it stands for or why it's AU? I've had a couple of students who've actually named their daughter this. And I had a kid who was in my kids' class who's named this. It stands for aurum, which is the Latin name for gold. So the ones that are ancient, which is copper, silver, and gold, the 7 that are in the Bible, actually 6 of the 7 that are in the Bible, they have their Latin names. Sulfur is also in the Bible. That's the hell and brimstone that's in there. But copper is cuprous, silver was argentium, and gold. Those are the 3. They're in the same family on the periodic table for a reason, and we'll get to that, I think, on the next page or the page after. They are based on their value. They're also based on their size on the periodic table. So copper is worth a penny, silver is worth a dime, and gold is worth a lot of money. And so gold is AU. So he took a piece of gold, and so this is gold, all right, AU. And I know silver and gold are not in the first 36, but we're going to run into silver and gold. You've all heard of silver and gold. Everybody's heard of silver and gold. And this was 1 micrometer thin. So that funny symbol is micro. It's 1/1,000,000th of a meter. It is the width of your hair. So 1 strand of hair, the width of it is about this thin. And that's the thing that's really cool about gold. You can pound it really thin. So I have a golden statue of Buddha that somebody gave me from Nepal, and it's actually not that much gold because it's such a thin layer of gold over him. But when he shot it at this, so the reason I have J.J. Thompson there, you don't have to write this down because it turns out this idea is considered incorrect now. J.J. Thompson discovered the electron, and he was considered this great hero, and he thought that this is what an atom looked like, that you had these big islands. He called it the plum pudding model because you had these islands that I had always learned that the islands were positive. The picture in my video, it shows them as negative, and I never know online what's right and what's wrong anymore. And then the electrons just moved around. They had not yet discovered the positive particles, but they knew there had to be positives if he had just discovered a negative. So he thought there were these big islands of positivity, and Rutherford wanted to prove him right. And so he shot the alpha particles at the piece of gold. And what he thought is anytime this positive came near these positives, he was going to get this huge boomerang effect of things going off all over the place. In the video that I made, the picture makes it look like that. But what he found, they all pretty much went straight through. In fact, 99, you don't have to write this whole thing down, but 99999, this is why I went on the board behind me, 9999999999999. Keeps going, keeps going. They keep adding another 9 like every year. That many went through. He didn't do it that many times, but they've now repeated it and they just go through. And so from that result, he can conclude that we're mostly, that's like an understatement, mostly empty space. Now it's not actually empty, but it doesn't have any matter. There's no matter in there. There's nothing. The size of this thing and the charge, nothing happened. It all went through. And so the guy, Rutherford already had his doctorate, so he didn't have to do the experiment. He designed it. And the guys who were doing it would come back and say, they're all going through. And he's like, oh, go back and do it again. One of those guys was Geiger, who made the Geiger counter. And I think it was inspired from this experiment because he had to keep watching and writing down in his notebook. And don't worry, Philip, you'd ask the question. I'm not going to make you do something like that in your kitchen chemistry where you have to keep repeating and repeating and repeating. Now, the second part was all of this went straight through, no deflection at all. The other thing was 1 in every 100,000, he would get a ricochet, but it would be huge. And in fact, 1 in a million, he would get it to go straight back. And so these huge angles told him that he had all the mass, virtually, say virtually all the mass. I'm used to writing on a board, so writing on a piece of paper confines me, and so my handwriting gets big. Virtually all the mass is concentrated. And he coined a term for it. He called it in the nucleus, or the center of the atom. And this virtually is huge. Again, this is 99.99999. It's most of our mass is all in this little space. So an example of what the size of the nucleus is, if you had a gummy bear, not a big gummy bear, like a little average size gummy bear, if that was your nucleus, the size of the atom would be a football stadium, the whole arena in 3 dimensions around this little gummy bear. All the mass of everything is the gummy bear. He's like infinitely massive, and everything around is empty space, pretty much 99.99999%, which is really cool. It's where the infinite potential that your thoughts create your reality, all of that stuff comes from this idea. We're going to focus on that 0.00001% right now. And we're going to talk about the subatomic particles. And again, if you have a question, just push your space bar and start talking or make a comment. I found in the Zoom environment, people don't make as many comments as in class.
I know you said we don't have to write everything down, but do you want us to be writing this on the paper, or are we going to be watching the video and then putting that stuff on this paper?
The video, thank you, Tiffany. The video, I comment, you don't have to write down anything from that. You're going to write a paragraph or 2 about your thoughts. Each of you is going to have a different part that inspires you. I do ask specific questions about the video, and this is one of them. And these are the answers. I asked, what are the 2 things from Rutherford's experiment that we learned about the atom? So, chemistry is the study of matter or atoms. Whoops. And the atoms are mostly empty space because they pretty much all went through. And when we got these ricochets, that the mass was concentrated. We did not have this plum pudding. Is totally wrong. We have the other model. I thought I had a picture somewhere. But you have this, and then out here are the electrons. It's hard to show it to scale because this dot would have to be like, you wouldn't be able to see it if we could draw it to scale. And in the video, I talk a little bit about the size of atoms and how small they are. So if you had in your hand like atoms, you would have like 100 trillion galaxies of stars of atoms. That's how small atoms are. So that is something that piece. There is also in the lab a little matching thing of names to what they did, and you'll be okay. You'll be fine. So we're going to talk about the subatomic particles. That's why I'll get the lab posted tomorrow, and you might want to look at it before Wednesday. So the part where you have to answer questions specifically, you can come to office hours Wednesday, or we can talk about additional office hours during the week. I think I have Thursday evening by appointment, and so you just have to email me and let me know, or Friday evening also. The particles are called, there are a whole bunch of subatomic particles now. Physicists keep adding more. Look at that, I just went into focus. As I got done with this page that I wanted to do on the board. The particles are electron, so that is the symbol. You'll always see me just write it usually like that, but that's an electron. The next one that was found was the positive one. And so these are all little case letters because they're really small. These are inside the atom. So one of the things in the quest for the building blocks of matter, they had this idea, Democritus, I talk about in the video. He was the first one who said, hey, well, he wasn't the first. It was actually somebody in India, and these guys got the idea from him. And this is in ancient Greece 2,500 years ago. We are built basically of pixels, what we consider pixels now of a camera. We're like this infinite number of little particles. And so an analogy I use, when you look at a beach, you see the whole beach, but as you get closer, you can suddenly see all the grains of sand. So the atom then, he didn't have the concept there was something inside the atom, and that's what Thompson and Rutherford did and totally changed everything. So the last century was considered the atomic age because we split the atom open and we found electrons. The P stands for, does anybody know? Starts with a P.
Proton.
Protons. Yay, look at that, that's great. What I found, real quick, because some of you are going, oh my God, everybody knows the answers, and I don't. About half of the students in this class have had some chemistry before. There's always one or two who've had quite a bit of chemistry, but they're going back for some other degree and they want this class for some reason. I assume that you've had no chemistry. And then there was a third one that has no charge, and they called it the neutron because it's neutral. The O end ending is the subatomic particle. So subatomic means it's inside the atom. It's inside every atom. So now they have muons and gluons and leptons and all these different things. And there's people who say, oh, it's only going to be this. And then they found the Higgs boson particle, and it goes on and on. What you need to know is just these three, because for what we do, these three are important, and what the chart we're going to get to. All right, and you need to know the charge. Electrons are negative, protons are positive, neutrons are neutral. So here's a question for you. Which one do you think was the last one discovered? The neutron, I'll actually tell you that the neutron was the last one discovered. It was actually almost 20 years after. It wasn't until the 30s. I think Rutherford it was 1911 that his experiment was done. And J.J. Thompson was right before the turn of the century. So why were neutrons the last one discovered? Any idea why they would have been the hardest to discover?
Because of their charge?
Because they don't have a charge. The positive and negative, yeah, so you're right. The positives and negatives are going to be deflected in a magnetic field because magnetic fields have poles, right? Positive and negative. And this is actually really important in chemistry because we will get into terms. Many of you have had biology and you've used the terms hydrophobic and hydrophilic. And that has to do, we use the terms polar and non-polar, that there's a pool. And so if there's a distribution of charge that is not perfect, you get a pool or a polarity. So like the North and South Pole on this planet. This is not their actual charge. Their actual charge is like 10 to negative 19 coulombs. We don't need to worry about that. In physics, they worry about that. All right, their relative mass. Protons and neutrons have a mass of 1. And it's an AMU. And back to the question, I think Tiffany had asked, like, what parts you need to know. The AMU, it's just, as I use it, that you're like, oh yeah, she's talked about that before. It's just a unit that's used by chemists to describe something that's really small. The size of an AMU, just more for reference, is about 10 to the negative 24th grams. We'll say roughly, that's roughly that many grams. It's like, I can't even imagine the size. 10 to the negative 24th, that many zeros. Like it's a number, it feels like they're making all this up. And that's actually the key to all this. This is why I have this quote here from Max Planck, that we pretty much are making this all up. And they declare them as laws to explain everything. When I teach, I start getting like really overheated because I have the door closed. All right. In the video, it's going to have a little chart, and it's going to give an incorrect piece of information. Most people teach that the electron has no mass. It is a particle of matter. It does have a mass. They've been able to measure it. Its mass is roughly about 1/1820th of an AMU. You don't need to memorize that number. You just need to know it's a lot smaller. It's about 2,000 times smaller. The analogy I give in my video is that the electron's like a little mouse. So you can draw a little, I can't draw a little mouse. It would have whiskers. How do you draw a mouse? They're little, and they have a tail. Looks like a cat. Okay, this would be like the size of a mouse. And the proton and neutron, they would be elephants. I'm not going to try and draw an elephant, but if you're like really bored, I think when I taught my son Joey this when he was like 4 or 5, we were in Yosemite Park walking through, and I talked about the proton and neutron as battleships. They were huge, and the electron was like him swimming in the water, that there's no comparison. And so that's why a lot of books teach that this has no mass, but it does actually have a mass. It's so tiny. This piece, the location, that is the big piece of information that I hope you get from this. And that is the proton and neutron are found in the nucleus. Again, the term nucleus was a word that Ernest Rutherford came up with. And it's about the same time that the nucleus of the cell is discovered. And I don't know which one came first. I know they inspired each other, and there's different books that say which came first. It doesn't matter. The nucleus is the center of an atom, and it's extremely massive. And the reason I said virtually all the mass is there is these guys are the elephants. So all the elephants are concentrated in the nucleus. The electrons are orbiting the nucleus. That's what quantum mechanics is about. This Rutherford, it actually took him 18 months to come up with this model from the experiment. He had only a slide rule, and the reason it took him 18 months is what you all know, without having to have any chemistry: negatives and positives attract. And he kept saying, if all the positive is concentrated, because they didn't know about protons yet, but if all the positive is concentrated in one place, how is the electron not crashing into it? Sorry, I don't know. Hopefully this doesn't get recorded. Yeah, anyway, really interesting stuff. All right, these two terms at the bottom of the page are what we're going to be working on the charts on the next page. So the Z and the A are a designation that I don't use because I don't know why they would call the mass number A and the atomic number Z, but somebody did. So the atomic number, when you have your periodic table, the atomic number is the 1 for helium to the 3, 4, 11, 12. That is the atomic number. Here for hydrogen, it tells you on my chart the atomic number. Every periodic table, like my one up here on the wall, everywhere on the planet Earth, the atomic number is on the periodic table. So I'll draw a box. Let's do C for carbon, and you'll see the number 6. It will be somewhere at the top of the box. Sometimes it's at the very top, left, right, doesn't matter. That is the atomic number, and the atomic number is the number of protons. Now, they gave them the atomic number before they knew about protons, but it turns out that's what it was. So I always tell everyone when we meet the aliens, this is our communication, is the periodic table, because every periodic table in the universe, carbon is 6 protons. So once you figure out how the aliens, what their word for a 6 proton atom particle is, then you can say, okay, that's carbon, and we can start translating. You can go with me there or not. So that is the number of protons. If it is neutral, and that is an if, it is neutral unless I tell you otherwise, the protons will equal the electrons. That is what makes it neutral. All right, the electrons can change, the protons cannot. The protons tell you what element you have. So the atomic number is the ID of the element. So carbon's just a shorthand way of saying any atom that has 6 protons concentrated in the nucleus. All right, the mass number is a challenge for the students who have some background in chemistry because this is often taught incorrectly. The mass number is not the mass. The mass number is the total number of nucleons. So there's a new word. And it's a word you're going to need to become familiar with because you're going to hear me use it over the next 2 weeks. So it ends with on, O-N, so it's particles. And the beginning says nucleus. So it is the nucleus particles, which are your protons and neutrons. So the nucleons are your protons plus neutrons. That is your mass number. Protons, neutrons, electrons, you can count, which means it's a whole number. It is not on the periodic table. So usually I'm on the chalkboard and I write this really big, and my other colors are not working of my pen. So I would put this, it's not on the periodic table. So if you did not print a periodic table up, I recommend that that is something you actually do. Find the time to go somewhere and print a periodic table or have one handy, or order one, like a poster, so you have one. Because we use the periodic table every single class. And so looking at my periodic table, there is a number underneath, like Ti is titanium, and says 47.90. That is the mass, not the mass number. If we go to carbon, it is 12.01. Or on my periodic table, it says 12.0111. This is the atomic mass. We're going to talk about this next week. This is an average number based on all the isotopes. Actually, I'll mention this on the next page. I just realized because I'll talk about isotopes. That is not the mass number. The mass number has to be given to you by me. So we're going to do practice on the next page, and you'll see how this all comes together. And then that's why you have homework for Wednesday, because you're going to need to try it. All right. So there we go. We'll walk through these together. And actually, at the bottom of these notes, I put a periodic table. This has the names in it, and this is the one I put up that you can print if you like, or you can find whatever one you like. All right, so this is how we write the symbol. I'm going to write the full symbol for calcium. The Ca is calcium. Learn the elements for the first 36. For that can be your goal between now and next Monday. There's these games you can play. You don't need to memorize them. If you have your periodic table, you just find Ca on there, and it's right here, calcium, and it's number 20. And that number 20 is the atomic number. So my symbol, I'm going to write it up here so I can write big. Usually I'm writing on the board. This, it gave you, this was the number there. That 40 is the mass number. The Ca is the symbol for calcium. If you wanted to write the atomic number in there, you would put it down below. And this drives some students crazy because they say, but on the periodic table, the atomic number is at the top. I don't know. I did not make up these rules. I'm just showing you how it's done. I leave the atomic number off because you will always have a periodic table. You need to have a periodic table. I have like 3 or 4 in this room. Like seems to be my life. All right. Because if you see the Ca, then you know it's calcium and you can get the number 20. The mass number, I gave it to you. It is 40. So something else, write in big letters above this chart, only whole numbers in this chart. We are counting particles. It's like counting M&Ms, counting grapes. You should pick a healthy thing to count. So if you're counting grapes, although grapes you can cut them in half, but something you can't cut in half. I'm trying to think. Oh, like a chickpea. It'd be really hard to cut a chickpea, a hard chickpea in half. But I'm sure you could. They keep cutting these smaller and smaller. All right, the protons. If you know the atomic number, you know your protons. Those 2 columns are always the same. And again, your worksheet, your homework, you get these charts again. It's just to see, hey, can you do it? The student, and actually on the midterm, you'll see one of these charts again, because it's just a nice way. It seems to be, it's actually a psychology experiment they did a long time ago. If they put kids even in a crazy neighborhood, like chemistry, but they put clear boundaries around them, the kids are happy to play. But you put them in this really prestigious, happy place, but there's no boundaries, everybody gets lost. So having charts are wonderful. All right, the neutrons. Actually, let's skip to the electrons. The electrons will be the same as the protons on this page, unless I do something funky, which I didn't do on this page. I think I did it on the next page, just to show you. The neutrons we find from the mass number. So remember, the mass number equals what? Always flip back to your previous page or wherever you are in your notes. And again, you can do this. It is the
Total number of nucleons?
It's the protons and neutrons, or the number of nucleons. So if we take the mass number and subtract the atomic number, you will get your neutrons. Now, this example, they all come out the same. That can happen. It doesn't happen that often. It's actually really uncommon. I do it so I look really smart when I do my subtraction. So most of these are numbers I can subtract in front of a whole group of people and look intelligent the first day. But that was something else I put in my email, and your calculator. And she walks off screen. All right. You know what? I forgot. I also told you you're supposed to put on your thinking hat. And so I brought my thinking hat. My thinking hat is going to fall over, but you should have a thinking cap. I have to fix my thinking cap. I'm going to have to use the other one. So you can think. Here we go. It's a rainbow thinking cap. We'll see it again. All right. I think you all could do 40 minus 20 without a calculator. Maybe you finished the chart. I was just babbling because some people finished the chart. Some people are fascinated by my babbles. S is for sulfur. Learning your element names makes it easier to get around. You start becoming familiar with the periodic table. But again, have a periodic table with the names so you have it as a backup, because in all honesty, half of your classmates are going to do that anyway. So you might as well all be in the same playing field. I wrote this one like this because that is your mass number, the 35. These are the 2 accepted ways to show the symbol. So always the symbol is the element, and either you write the mass number before it as a superscript, or you say it like this. The second way with the sulfur is how we always read it. So sulfur 35, or the first one would be read as calcium 40. I think there's a homework question that says show the 2 different ways to make the symbol, and that's all I'm talking about. All right, so we find sulfur, and sulfur is way over on the other side of our periodic table. And over here, number 16. Again, if you learn the names, you start becoming familiar with where to start looking. If you do all the work, you become pretty good at this. So that's the atomic number. That is on the periodic table. So the atomic number, I'm going to write PT for periodic table. What other columns do I put the 16 in?
Proton.
Always the protons. Thank you, by the way. You guys are being amazing participants. And we're going to put in the electrons. Because I didn't tell you to do it otherwise. All right, we do not put it in the neutrons this time. The neutrons are not 16. We would have to take the mass number, subtract the protons, and that will give us the neutrons, which will be 19. Because these two together equal the mass number. So there is a word that appears on the 3rd page, and I'm going to skip to there for a moment. It was supposed to be on this page, and then I had a formatting issue. And I was like, oh, it won't matter if it's on the 3rd page. An isotope means that you have the same elements, but they have a different mass. So it would be another sulfur, but we'd have a different mass. And the reason I wanted to mention that, so there's and we'll come back to this. On your periodic table, if you have one, you'll look down here and you'll say sulfur wants to be 32.064. That's the atomic mass, not the mass number. The atomic mass is an average of all the isotopes. So sulfur 32 is probably the most common isotope, but that's not the one I was talking about here. So when you're asked to fill in the boxes, you have to fill it in based on whatever one I'm asking you about. And again, you'll have some in your homework that I will go over, and we have another page of these to do. All right, so the next one, I gave you the protons. So if I give you the protons, that number goes as your atomic number. And then actually we can look down here, we find number 17, and 17 is Cl. And does anybody know? You can like get your little magnet. It is chlorine. This is what we put in our water to kill bacteria. All right, we have fill in some more. We put a 17 somewhere else. What else gets a 17?
Electrons.
Electrons, thank you. So some of you guys have all got this. So we have one more piece, which is the mass number. So we just add these two columns up. The protons plus the neutrons. So like what I wrote up here, protons plus neutrons give us 37. So again, if you look at your periodic table, sorry, the periodic table I usually give out, maybe I'll post that too. It has bigger numbers because the numbers we work with a lot. But you can see here that the number is 35.453. Go with whatever number I give you. You're not going to use, these are all whole numbers. Go with it. I'll talk about more on the next page. All right, next one is 79. We already talked about 79. That's AU, and that is gold. There are several of you who look like you might be from other countries. If you can go with the English name, that'd be great. I'll call it gold. I do sometimes have students use the Latin name, and that's fine. I'm not going to mark you wrong. So if you know it as aurum, because that's how you learned it. All right, protons will be the 79. The electrons are going to be the 79. And then, can you get your handy dandy calculator out? and subtract. So the 197 minus the 79, and I think we get 118. Is that right? Yay. All right. Now, there's usually a question somebody will ask me. It has to do with my symbols. I just said, what's the element symbol? I didn't say write the full symbol. So I'm okay with you. I'm just looking to see, could you identify it as chlorine and gold? But if you like to do for practice, you can also add your mass number. And so you write it as a superscript. And for the gold, we would write 197. So again, that's the mass number is what you show there. If you want to show the full symbol, you would also write the atomic number, and it's shown below. So some students we actually will start doing this next week because we do nuclear chem. The mass number minus the atomic number will give you your neutrons. All right, one more. It is not element 70, and it is not element 120. What element is it? It is tin. Tin is a sin. So tin is one of the biblical ones. Sanus is its name. And so as students, and that's how they could remember tin, tin is a sin. It is because if you take the 120 and you subtract the neutrons, so the 120 minus the 70, we would get 50. And that is going to be your protons, that is going to be your electrons, and that is going to be your atomic number. We find number 50. Tin is actually pretty special. And if you want to show the full symbol, you can put the 120. You can write just the 120, or some students like to write everything. Great. All right, questions. So
I have about the electrons. Why are they all the same in these examples?
on the next page, can I answer that on the next
Yes.
page? I think that's you, Jennifer. I actually made one on the next page that was not neutral. They are the same on this page because a lot of students, this is overwhelming. It's the first day, but I think having a whole extra week off, we're all like just ready to learn again. Let's just do something in this environment. All right. Thank you. And on the next page, I did that on purpose because people always ask that question. Keep it neutral, keep them the same unless I make them different. And so actually, if you look at the next page, if you look at the box, the second to the bottom one, you can see I made 47 protons, 46 electrons. And so I'll show you what happens when we get to that page. So unless I make them different, keep them the same. And actually, after the first midterm, we go into the whole world of ions. And so that makes them an ionic compound, which is actually what everything pretty much is. I have a comment here. Learn your first 36 elements. Learn them. Learn the names. You don't need to remember the order that they're in. And again, sorry, I had been anticipating I would stand up at the board for the first 2 pages. Yeah. All right. So learn them. And there's even a song. I think I put a bonus on the lab if you want to sing the song. Nobody's ever done it. I had some people who said they were going to. You can make a video recording of yourself. There's actually a couple different periodic table songs. And just send me the YouTube link. You don't have to do it for the whole class. So I had a student last term who played the ukulele, and so she made me. It was really awesome. All right. Periods and families, we need to talk about that. And periods are horizontal, families are vertical. Talking about the periodic table. So when you're going across, these are periods. Hydrogen and helium are in the first period. Lithium, beryllium, and across to neon, they're in the second period. Sodium across to argon, they're in the third period, and so on. Special K, potassium over to krypton. Kryptonite was named after Krypton because they had just discovered Krypton, and the guy who wrote Superman was so inspired by the discovery of the noble gases, he named it kryptonite. pretty cool. There's all this history. There's actually a video on the comic book history and the periodic table because there's a big connection between them. So if you're into that. This is why you want to learn your element names, because you hear me say potassium and your chart has a big K. You want to know why I'm writing K. You're like, what is she talking about? All right. Families are the key. And I talk a little bit about this in the video. Dmitry Mendeleev is the guy who put together the periodic table. I have a picture of his periodic table, and then I have, well, we have ours. Families, they were put into families. They're like hearts and diamonds and spades and clubs and, I don't know, daffodils. So they, families behave similar. In their chemical properties, in their chemical reactions. So people had been doing chemical reactions and keeping data for a while, and it all was just kind of mishmash, and he organized it. There's something I forgot to say at the very beginning, and that was because I didn't have my big space. I think he fell off. So normally you walk into the classroom and you see this ginormous periodic table, and you're like, chemistry, periodic table. And like Tiffany was here early and we were talking, and she got a periodic table she has above her desk so that she learns this. And sorry, I have a funny shadow showing up there. My comment to my class always the first day is look at your that periodic table. Look at it in awe. And then on the last day of class, I will hopefully remember to tell you, look at that periodic table again, and it should look totally different to you as you realize there is so much going on that table. And so if I'm doing my job of serving you the mysteries of this periodic table, and not only that, you become extremely geeky. So over Thanksgiving, when everybody's wanting to watch football, you're like, no, I want to watch the science documentary, and you start explaining stuff to everybody, and they're like, okay. So that's my job. So he put them in families based on their reactivity. And so these columns up and down, they're also called groups. So you will hear me sometimes say group or family. And we're going to learn names of families. Oh, wow. I just realized my numbering is different than how I always did it. All right, this first column is really important, and they are called the alkali metals. Does anybody know what the word alkali means? You all know what the word metal means, I'm assuming, right? Like gold, silver, and copper, and titanium, and platinum. Alkali means the opposite of an acid. It's a base. And so if you drop any of these into water, you get sodium hydroxide, potassium hydroxide, you get the bases. It's what they made soap with. All right, the second column is called the earth metals. So they sometimes will put the word alkaline in front, which is the same as the word alkali. I don't know why they did that, but you will always see the word earth. So I usually just call them the earth metals. I'll put alkaline in parentheses. So like some of you, you have a first name and you don't go by it, you go by your middle name. This column, they're common in the earth. They're found in the earth. They're actually usually found as a solid in a compound form. A lot of our gems, beryllium, if anybody's into gems, I'm pretty sure ruby is beryllium and something else. All right. The middle here, this big divot, we're going to see why it looks like this over these first 3 weeks. The periodic table will look totally different by the first midterm. That should be like you have to write an essay on the first midterm and tell me everything. These are called the transition elements. And they do something really special, and we'll learn about them when we do quantum mechanics. I wanted to mention while I'm thinking of it, these two rows down here, they do fit in. There you can see a gap, and here you can see a gap. But if we put them in there, then it'd be really long and small, and it wouldn't fit nicely on this piece of paper. And so everybody always pulls them down, even on my table up behind me or the one underneath. And we'll see that as we go through stuff over the next 3 weeks. All right, every column has a name. I don't know the names. I don't expect you to know the names. Google, I'm sure, has names. We need to know these first two and the last two. So what is being numbered is 17 here. These are called the halogens. And you may have heard of halogenated hydrocarbons. They are the ones, the CFCs, that depleted the ozone layer. All right, and then column 18 is the noble gases. So I often write this wrong and write Nobel, like Nobel Prize, but noble means inert. So that's an I. And I'll ask my students, what does inert mean? And somebody will go, well, it means noble. In some periodic tables, mine don't have it. They'll actually say that above that column and they'll label it as that. Inert means non-reactive. These guys are in a state of bliss. They are not in Mendeleev's original periodic table. They weren't discovered until about 120 years ago because they don't react. So the elements were discovered based on their reactivity, or something I talk about in the video, their transformations. Noble gases are perfect. They are all reacting to become a noble gas. And that's what this term is about. They all want to be in that state of bliss, of non-reactivity, of serenity. Halogens are extremely reactive because they're right next door to perfection. They will do everything in their power. They are extremely reactive. That's why we're learning the name of them. If you ever run into a halogen, you take caution. It's why we chlorinate our water, because it's so reactive. It kills the bacteria, and it's desperation for one more electron. And we get to all of that as we go through the term. Something I want to mention, and you'll hear me mention this throughout the term, the periodic table is like the globe. It is not flat. We flattened it to fit on this piece of paper. Pretty sure you all know the Earth is not flat. We have pictures of it from space. The periodic table, though, is not a globe. It is a spiral. And so if you look at number 10, neon, it's right next to fluorine. Number 9, it's also right next door to number 11, sodium. So there are periodic tables. I put some in homework sets and worksheets, and they freak some students out, but there are other ways of showing the periodic table. They're actually better. There are these three-dimensional ones that are really cool, but we're going to work with this flat model. And so those are the names of the periodic table. You'll hear me use those names, so become familiar with them. All right. Let's move to the last page, and I'll probably go past 8 just because sometimes I do that. If you have to leave, you can leave. I just keep going until I get finished. Was there any questions? I'm good in this format. You just have to start talking because I don't see everybody.
Quick question.
Go ahead.
So you're recording this lecture, right? And but you also mentioned that you already have videos posted. Are those these same lectures but recorded from a different term, or what are those? What's the difference between this recording and the ones you've already posted?
When you go on, you'll know. So the one is a bonus opportunity to make a healthy change in the month of October that I usually end this. So normally this class goes until 9 o'clock at night. So I usually have another hour. One of them is the history. So that page, that first page I went through really fast right here. I usually spend a half hour talking about the history of the periodic table. So I made the video and posted that. So it's often, this is an awesome question. We normally are here from 6 until 9, and I thought nobody's going to want to do that in this environment. It's so long to be on Zoom and me talking like this. So I often make parts of the lecture there that are not here. So it's more on the history, and there is an extra credit bonus that I offer for the month of October. So just watch it sometime this week. The third video is a pre-video for Wednesday's class. It's about the math that we will be doing. It doesn't matter if you watch that video before or after the class. The notes are in lecture 2. So I hope that answered your question.
Yeah, it does. Another quick question. The link to your YouTube page we can find on Blackboard, is that right?
It is, and I'll repost the syllabus with that and fix the Saturday. There's probably other mistakes. Oh, you know what? I'll repost the syllabus at the end of this week because I want people to have a chance to give me feedback by the end of the week if they want another office hour towards the end of the week. It usually takes us the first 2 weeks to figure out how we're going to manage our time. And so I don't think you all know exactly what office hours you're going to want to use quite yet. So please know I can be open to an office hour Friday or Saturday. I don't really want to do both, but we can figure it out as we go on. And so thank you. And the other comment I wanted to make, your questions are awesome because everyone will have these questions. Is you kind of have to trust me as we go through the first 2 weeks. I try to be consistent and you get in the groove. And once you know how a class works, it works beautiful and you can follow along. And we had a joke that there wouldn't be any snow days, but there was a smoke week. All right. The other comment I wanted to make is I think there's a lot of notes going on in the chat and I can't see it in this format. I possibly will remember to look after, but if you were writing something in the chat that you had a question for me, make sure when we get done that you ask me. All right, so this was the page about isotopes.
Just so you know, the video is kind of blurry right now. It's really hard to see the paper.
That work?
That's better.
Yeah, I'm like striking out tonight with blurry. Like now you can see behind me. The gnomes are being really mischievous tonight. All right. That's actually, and thank you for saying that. That's why it's really nice to have them printed out so you can write on. I know not all of you have printers. The school supposedly is going to have, I don't know, they have a place you can print there, possibly. I don't know what's going on. There's other places you can see, but thank you. All right, so isotopes, again, same element, but different mass. What that means in terms of subatomic particles, if they're the same element, they have to have the same, and they all said protons. So they all have the same protons. But if the mass is different, they have different neutrons. I'm not even caring about the electrons here. Same protons, but different neutrons. An example is right here, chlorine 35 and chlorine 37. So they're both chlorine. They get the symbol Cl. They both have 17 protons that we know from our periodic table. So chlorine's right there. But I gave you 2 different masses, 35 and 37. So using our periodic table. Oh, this one's going to be blurry, but you can kind of trust me on this. If we look at our periodic table and we look at chlorine, which is number 17, underneath it usually says 35.45. Some periodic tables will say 35.453. Some will say, this one probably is crazy. Oh, it's got the 453. All right, this number is the average mass based on isotope abundance. Wow, that's a mouthful for your teacher. You're not going to be asked to like give me the definition. This is to help explain it though. Now, if you had a number 35 and 37, and I asked you to average 35 and 37, pretty sure without a calculator, you would all get 36. The average of 35 and 37 is 36. However, on the periodic table, the average of 35 and 37 comes out to 35.453. And that is because chlorine 35 is more abundant. It's not a 50-50 mix of the two. You have more of the 35, so the average is pulled towards it. There's a question on the homework with this, so you can think about it. Now, the question I then ask is, how many neutrons are in the more abundant isotope? Well, we figured out chlorine 35. The more abundant one is always closest to the average. And then we take the 35, which is the mass number, and we would subtract the 17 protons, and we will get that we have 18 neutrons. Now I mention this because your like worksheet and stuff is fill in the blanks, and a lot of students will do it really fast and haphazardly. Same like your midterm, and students will do it really fast and haphazardly because they didn't read my whole question. So sometimes I ask you which one is more abundant, but sometimes I'll ask how many neutrons. So make sure you read my question and answer the question that I asked. So the answer here would be 18. All right, we're gonna do practice now. So you need a periodic table of some type, and gosh, I wish I could do a split screen. We're gonna do the 4th period earth metal. So remember we numbered down, so 4th period, and the second column was the earth metals. So that puts us to Ca, but I want the name and the symbol. So Ca is calcium. This is my attempt to get you to learn element names, because I'll be writing with symbols because it's a lot shorter, but I'll be speaking element names. And so you just have to, you guys have to be forgiving of yourself. You are learning a whole new language today, the chemistry language, this whole term. And so we have to learn how to speak chemistry. And so I'll be writing in symbols, but saying words. And so that's why you want to become familiar with the first 36 and then a handful more. All right, 4th period and group 4B. So this is a problem I didn't anticipate until this periodic table only did A's and it only did numbers. It is a new way of numbering the periodic table. My placemat from OMSI, you can see there's A's and B's. So we're going to switch to that. You can, on Google, I'm going to post one that has A's and B's. I'm pondering things. There we go. 4B, 4th period. This OMSI's periodic table, their placemat's awesome. And it's, you could like write on it and then clean it off. It'd be like awesome. Get a laminated placemat periodic table. So 4th period 4B is Ti. It is not tin. Tin is a sin. Tin was, sorry, this is titanium. All right. Oh, this one, E. I'm circling it. I wish I had my pink pen. I don't know what I did with it. Putting a star. All of these questions you need to be able to do. Similar to sodium. So first of all, you need to know which element is sodium, and you're going to become really good at this over the next 3 weeks. So by the midterm, you're like, oh, sodium, Na. There it is. Similar properties. Anybody remember? I actually mentioned this. It's how Mendeleev made his periodic table.
Families.
Yeah, families. So whatever one you know how to spell, oh, you guys all have, it's like right there in front of you. So you can pick lithium or you can pick potassium. You know, OMSI's placemat is freaking amazing because I just realized something else. Hydrogen is always shown with this family, but if you notice on this one, there's a gap because hydrogen is not an alkali metal, but it's always shown there. So you can pick lithium or potassium. I'm gonna go with special K, potassium. I had somebody who could remember potassium is really high in special K. Terrible source of potassium, by the way, because it's highly processed. Don't eat special K. It's really loaded with sugar. Best source of potassium is actually sweet potatoes, and it's sweet potato season. So bananas too, but sweet potatoes are quite a bit more. All right, halogen in the 5th period. So I went beyond 36 because you guys have your periodic table, 5th period, halogens are over here, and we get I. I is not iron. Does anybody know? I is, your thyroid is very happy when you get this one. It's iodine. Iodine actually means purple because the flame is purple, or the gas when it becomes a vapor is purple. All right, 3rd period, alkali metal. So alkali metals are first, and we go over 3rd row, and we're at sodium. So this is just practicing with the family names and the symbols. All right, unreactive.
Noble gases.
Yeah, the noble gases. And then, oh, I forgot to mention this. This is why I have this question here, because I always forget. So we're going to go back. The 2nd page, periodic table, or whatever periodic table. Again, this OMSI placemat's awesome because you can write on it. There is, actually, I'm going to use the OMSI placemats because this periodic table is, I did not print in color. If you have it in color, you actually will see this. So there is, and actually the one behind me, it shows that there is a staircase that happens. I'm going to draw it in on this one. So it's here, boron, silicon. It goes next to arsenic and germanium, between antimony and tellurium, and goes on. That staircase, this side is the metals, and this side over here is the non-metals. Metals just mean we can make them into something pretty. They're lustrous. They conduct heat. They conduct electricity. Non-metals are brittle. Most of them are gases. They are not metals. You guys know what metals are. Non-metal means it's not a metal. The staircase, if you touch the staircase on 2 sides, not a corner, a side. So like boron, silicon, arsenic, tellurium, they are called semi-metals or metalloids or metalloids, depending where you come from. That would also be germanium or arsenic. So it could be under the staircase. So antimony, polonium. I wanted to mention aluminum. This is a problem with our periodic table because we took the spiral and flattened it. Aluminum is a metal. It is not a semi-metal. I don't ask that question because I think it's a trick question. So a 3rd period metalloid is silicon. And they are called, I actually like the term semi-metal better because I can say it. Silicon is Si. Because they're the semiconductors. So they conduct electricity, but in a different way, and we can use them in our computers, and that created the technology age. The other one I wanted to mention, just this is another history thing. At is Astantine. It is the only element on the periodic table with a feminine ending, the INE, because it's so unstable, and apparently you can't even look at it or you'll become blind. And so they gave it a feminine ending. And so it's just one of the beautiful histories in the periodic table that I love, because it was, you know, people are afraid of the things they don't understand. All right, let's go ahead and do the chart. I'm going to walk through it. And again, if you have to leave, it is 8 o'clock. But take a deep breath. Let's walk through it. And go back and do it again. So pull up the notes. And even if you can't print, just pull them up and try it again and then check your answer key. So I gave you the sodium. So Na is sodium. And again, I'm doing a lot of element names today because you want to become familiar with them. So the more you hear them from me, the more you become familiar, the more you become inspired to do more of these. All right, sodium. Atomic number, we find it on here. It's number 11. And that 11, atomic number is your protons. And then back to the question. It is your electrons unless I make the electrons a different number. So I will give you the number of electrons, then you know you have a different number. All right, the mass number I gave you, that's the 23. We need the mass number to find the neutrons. So mass number minus the atomic number of the protons. All right, next one, P. Go ahead.
When you change it, like for the very last one, when you said it'll only change when you change it, does that still mean that the protons are going to be the same regardless of that changing?
Yeah, sure. Let's skip to that one.
Sorry.
No, you're good because so here I gave you the atomic number. And this is actually a really great question that several of you are anticipating. The atomic number is your protons. That is absolutely the point of everything. The electrons can change. When the electrons change, it's still number 35. 35 is Br, which is bromine. What happened though is because we have an extra electron, so we, right, instead of 35, we now in the symbol put a negative, and that negative says I have an extra electron. So that's what it means. That is getting into the realm of ions, which I expose them to you because they're actually, most things are ionic, and because everything has reacted to become like a noble gas, and we spend like a whole week on them, I think in the 4th week. So yeah, let's finish this row. To find the neutrons, always just subtract 79 minus 35, we get 44. We'll just move up. So like on the next one, it is the 47 that tells you the element. 47 is our atomic number, and that is Ag. Anybody know? Ag? I mentioned it before.
Silver.
It is silver. It is named Argentium because they thought Argentina had a lot of silver, and it didn't. It just had to do with the Incas. Peru has a lot. The protons plus the neutrons, so the 47 plus the 60. You don't have to write this. I just want the final number in there, 107. Whatever you get, that's the number, not on the periodic table. Atomic numbers on the periodic table. Now, this time we lost an electron. So should have been 47, but I suddenly said, hey, there's only 46. So if you gain an electron, if there's an extra electron, we're negative. If you lose one, you're going to be positive. And we're going to learn how to do that in the 4th week. But for now, if I give you a different number, that's how you would do it. All right, let's go back up to the P. 35. P is phosphorus. This is a capital P. The elements symbols are always a capital letter. The old ancient ones often only have one letter, like phosphorus, potassium, carbon, oxygen, nitrogen. It is a capital letter. If they have 2 letters, like calcium, first is capital, second is lowercase. When you write the name, I don't care if you use capitals or lowercase. When you write the symbols, I do care. All right, phosphorus is over on the other side. It's up here, it's number 15. element symbol, sorry, element mass number I gave you, that's the 35. And so I think you can all do this. The atomic number is the protons and it's the electrons. Subtracting the mass number minus the protons, we have the neutrons. All right, the next one, I gave you the protons. You make that your electrons. You make that your atomic number. You look at number 33, and it is AS. You add the protons and neutrons together to get 74. So if you want, you can show the full symbol like that. Anybody know what AS is?
Arsenic.
It is arsenic. All right, we got one more. So mass number minus the neutrons, we get 22. And we put the 22. Protons, electrons, atomic number are all going to be the same. 22 is Ti. We talked about that earlier. Ti is titanium. Hopefully none of you have that in your body because that would mean you had to have a hip replacement or a knee replacement or an ankle replacement. And again, in this column, I'm okay with just the symbol, but some students like to show the mass number. That's up to you. All right, I want to do this one because it's a question on your homework like this. And it's always students struggle with it. So I thought I'd do one in class. It wants you to look at each pair and figure out what those two elements have in common. And let me see if I move this closer. There we go. Look at that. Well, what these two have in common is they both have the number 60. So if the mass number is 60, they have the same nucleons. So that's our answer. Again, nucleons are what's in the nucleus, the neutrons and the protons. All right, I'm going to skip to C because that's easy. They're both carbon, so they must have the same protons. But that wasn't one of the choices. So they have the same electrons. So I'm going to change it to electrons, protons and electrons. All right, now we're going to look at the middle one. They are not the same element. So not the same electrons. They do not have the same mass number. So it's not the nucleons. So if I fill in their atomic numbers, argon is number 18 and potassium is number 19. If you take the mass number minus the atomic number, we get 22 neutrons and 20 neutrons. Well, that's not the same number, so it's not the neutrons. So we're left with only one choice. And it's something I didn't say, and this always freaks people out on the homework. Oh my God, she asked questions she didn't teach us. What's she doing? I'm asking you to think a little bit and deductive reasoning that you could figure it out. Total subatomic particles would mean protons plus neutrons plus electrons. So how can we figure that out? Protons plus neutrons is your mass number. And the electrons are your atomic number, assuming it's neutral. So the mass number plus the atomic number. Again, the electrons can change, but I'm not going to do something like that to you on a question like this. So if we go back, let's cross out that. I need another color. 40 plus 18 gives me 58. 39 plus 19 gives me 58. Same number. So same total subatomic. I always giggle with this question because there's so many other subatomics, but we're good. It's the same. All the other ones are parts of these. All right, it's a lot. I'm tired. Questions? So your homework again, if you have the ability to print, great, you can print. If you don't, just do it on notebook paper. Your study set, I'm just looking to see that you made it your best effort. And then I will go over it Wednesday. It is due before class on Wednesday. I will go over it. You make corrections. I'm not going to correct your homework. I just look again, see if you did it. Your worksheet is due by midnight on Wednesday. And I am willing to go over that with you before class or after class. So I will have office hours at 5 o'clock. And if it's a test, if people need me, I can be here earlier than that. And I can stay after. And I can actually stay after today. If there's no questions, I'm gonna.
I only have one because I'm super tired.
Go ahead.
Wednesday midnight, so like 11:59 before Thursday or 11:59 on Tuesday.
11:59 before Thursday. 11:59.
Okay.
It's
Sorry.
Wednesday. Yeah, thank you. That's why it says 11:59 p.m. because midnight confuses everybody. All right. I'm gonna. If there's no other questions, I'm gonna stop my recording.